let us do the summation. Yeah, this one. Yeah. So we simplify. This is the summation we need to calculate. Based on this structure, S equals summation of these terms. So we need to explore, we need to take advantage of the special structure of all the terms. All right. All the denominators are power of 2 with consecutive powers of 2. So this special property, we can take advantage of it. So that is when we multiply the whole thing by 2, we have the similar structure. 2s equals all the denominators still power of 2. So then the numerators, you will see the numerators look slightly different. If you compare these two lines, S expression and a 2s expression, you can see for the same denominator, same power of 2 denominator, the difference of the numerator is 1. So next pair, the difference of numerator is 1, and so on, all the way down to the end, to infinity. Yeah, no end, to the infinity. Yeah. So this is a good property we can take advantage of. Now let's do subtraction. 2s minus s. From the left-hand side, we get s. Right-hand side, when you do subtraction, you will see this summation is much easier to calculate. In each big circle, you will get a reciprocal of power of 2, right? So the whole summation, you will get consecutive reciprocals of power of 2. Then we know it's a geometric series, right? Yeah. So this is a geometric series, and we have formula to calculate summation, infinite series. Yeah. The formula, the first term, 1/2 over 1 minus the ratio between these two terms, a common ratio. The common ratio between two other adjacent terms, that's 1/2, another 1/2. Okay. So 1/2 over 1/2, so the final answer is 1. S equals 1. This infinite summation equals 1. Okay, yeah. So then we can estimate building process. This major part. The minor part, very little. We can ignore. The major part, because remember, we factorize n out. After we factorize n out, inside the big circle summation, it is 1. Then we put it inside. So big O of n, then it's acceptable, right? So not a big O of n squared, not a big O of n log n. N log n, not acceptable. Not acceptable. But the n, only n, then it is acceptable. Yeah. So now, this special method could be used. So the cost is not very high. All right. So after this step, we can keep going. We can go to the next step. Do the heap sort. It's pretty easy, pretty straightforward, because we have done so much comparison work. So the last step, not much work to do. All right. Yeah. So the second summation, compare with the major part, very little. So we can ignore. All right. 8.7, heap sort and efficiency analysis. So let me describe the heap sort first. So let's look at a typical max heap after the building process. So we assume we have a max heap. The max heap, one immediate property, the maximum value must be at the root node, right? The maximum occurs at the root node based on the max heap property. All right. The largest element is at the root node. So when you start, so after the building process, the maximum is at the root node. So you know it. All right. Then you can put the maximum in place immediately, right? Put it in place. All right. How to put it in place? Its right location of the maximum is the end of the array, right? The last position of this array. That is the final position of the maximum. But the position for the root, it is the first position. The root position is the first position in the heap. And its destination position is the end. So it's different. So you need a one swap operation to put this root element in place. All right. How to put it in? Swap. Yeah. Let us use this one line segment representing the whole array. And we store the max heap in this array already. Currently. Yeah. All right. So now we start heap sort. The heap sort, we need to swap the root element, first element, that's the root. It holds the maximum to the last position, right? And this position, the last node, that position is the final position of the maximum. So we need a one swap operation between first location and the last location. Just one swap. We put one element in place. Yeah. Okay. Yeah. But after that swap, the node, you put it at the root node, would break the max heap property, right? Because after that swap, you won't get a max heap. There is a violation at the root. There is a violation at the root. It's definitely a violation. But other places, no violation. Other places, it's fine. The only violation occurs at the root. But we can run max heapify operation. We can fix the violation, right? We can fix the violation. After we run that max heapify operation, to fix it, it becomes a max heap again. Okay? Yeah. So after we get a max heap again, we can put the root node in place by another swap, because we know it's right position immediately. By another swap, then another fix, another swap. So we keep doing like this. At the end, we will put all the elements in place. That's the heap sort. Here, let me use the simple pseudocode to describe the whole processing process. First, swap A of 1, the root node, and A of n, the last element. After that, we put the max in place. Then we need to recover the max heap property. How to recover? We run max heapify, right? Run max heapify. After that, we do recursion. So we can complete the whole process. All right. Procedure of heap sort. Iteration. So we do iteration. All right. When we start, here I look at the whole procedure of heap sort. So when we start, we build a max heap. That step, building step, we only do once. Building step, we only do once. After that, we get a max heap. We can run iterations. All right. For loop, I from n down to 2. Because last element, we do not need to. The last element, we can drop it in place immediately. So down to 2. All right. Swap A of 1 and A of I. Because I from n down to 2. The current location I, so that's the end of the current array. So we swap root node with the element at the end of the current node. Then we need to reduce the size by 1, the heap size by 1. Because we just put one element in place, so we can exclude it from consideration. After size reduction, then we need to run that max heapify operation at root location. So this 1, index 1, is the location. Where do you want to start max heapify operation? This location. After that, then, so you move to the next iteration of this for loop. After you finish the whole for loop, you put all elements in place. How simple it is. That's the heap sort. Okay? Heap sort. Next, we will see efficiency bigger of n log n. So we will see that. In a very easy way, we will see that. But before we see that efficiency estimate quickly, I want to say something about remember our second requirement. The algorithm must be in place. That means the extra space used must be bigger of 1. Now, we need to check this property in place, if this algorithm is in place or not. All right. So one thing I mentioned before regarding the in-place algorithm, the extra space used must be bounded by some constant, that requirement. That's the key requirement for in-place algorithm. All right. Now let's look at the recursive algorithm. Recursive algorithm. You can see, because in recursive algorithm there is a very important internal process. That is, you need to use a stack in memory, right? Yeah. Inside implementation, you need to use a stack in main memory, and the stack could be very deep. The depth of the stack could be very deep. That if the stack is very deep, then it consumes a lot of memory resource. It could be out of control. The stack could grow very deep, out of control. In that situation, how can you say the extra space used is bounded by constant? Right? So not bounded by constant. So that means when you use recursions, in general, the algorithms cannot be in place. So you can see this requirement is pretty strong. Yeah, because your stack could be very deep. Right? So although for each device step, if we use quicksort, we look at the partition step. Each partition step, it is in place. Just one partition, it is in place. Yeah. So you swap, so you do not need a lot of extra space, bounded by big O of 1. But when you do conquer, you need to do recursive function call. When you call your function recursively, you need to use the stack. The stack could be very deep. So then you may not be able to control your extra space used bounded by constant. No, you cannot. So that kind of problem you need to be aware of. Yeah. So here, look at here. For loop, right? Yeah. For loop and max hippify. Yeah. This for loop, no recursion, right? Yeah. Swap, these two lines, no recursion, right? Yeah. But max hippify may contain recursion. Yeah. If you look at our previous, so it may contain recursion, but if it relies on recursion, you may need to replace it by iteration. Yeah. Because this maxima, you do not have to use recursion, right? Yeah. So it is pretty easy. You can use the, for loop or while loop to implement max hippify operation. Yeah. You do not rely, you can avoid recursion easily. Yeah. So this step, you should replace it. Yeah. So here, no recursion. In order to get in place algorithm, no recursion. Yeah, no recursion. All right, yeah. And another place you need to avoid recursion, this build max heap no recursion. Otherwise, you cannot control your memory, right? Memory resource, out of control. Yeah. If you take care of these two steps, non-recursion implementation, iterative implementations, then at the end you can say you have an in-place algorithm. So that's the point I want to convey here. Yeah, you should be very careful. Okay? Yeah. Otherwise, you use a lot of memory resource. So you need to be aware of that. All right. Okay. Yeah. So after this discussion, the last thing, analysis part, it's pretty simple, so we can see it quickly. Because, look at that. Every time you put one node in place, because there is a swap, you fix that, you consider the worst case, right? Yeah, because we look at the efficiency, we look at the worst case. The worst case, you run the max heapify from the root to the very bottom, that's bigger of n log n. Yeah. Could be n minus 1, but we just use log n. Okay, all right. Next one reduced by 1, so the next term log of n minus 1. So consecutive log of sum of consecutive log integers. Yeah. All right. Then each term, look at that. Each term is bounded by log base 2 of n, right? The second term also bounded by log base 2 of n, and so on. The last term bounded by log base 2 of n. Total, you have n terms. Actually, n minus 1, right? N minus 1, here we use n. So you can see the last one, the last thing, yeah. So the whole summation bounded by bigger of n log n. So this is a very generous estimate, very generous. Each term we enlarge a lot. Near the end, we enlarge a lot. Okay, yeah. But we get a bigger of n log n. Yeah. There is some better estimate. Yeah. There is some better estimate. Yeah. Yeah. Better estimate, we need to use the integral. Integral. Definite integral. Right? Yeah. To estimate. Yeah. Yeah, but here, even that, you use better estimate. You get bigger of n log n. Same category, but the constant is slightly better. The constant will be better. Yeah. All right. So that's this topic, heap sort topic. All right. So we have half an hour left. Let me do a quick introduction to the hashing. Yeah. So this topic, very important, very useful. Although we do not have much time, but I want to give you some high-level idea, because the knowledge of this part will be very useful. So I want to talk about the main ideas there. Yeah. All right. Let me switch my PowerPoint slides to part B, hashing technique. right. Part B, yeah, part A. It's my part B. Huh? All right, yeah, hashing, yeah. All right. Change my pen color. All right, yeah. Yeah, so review we will do Monday's class. Yeah, so today we do a short introduction. If we couldn't complete today, so next time I try to complete quickly. Yeah, so because after this class we only have our last class on Monday, and we need to review homework assignment number 2. The main part is homework assignment number 2. Yeah. So I need to control, using at the most 20 minutes in our Monday's class. Yeah. So after that, then we do the review for the final. All right. Yeah. Why using hashing? Yeah. So this technique is very important. Yeah. So I give you the main idea. Let's recall a problem we solved before called the element uniqueness problem. Element uniqueness problem. Yeah. Given an array, containing, arbitrary numbers, we need to run a function to check if the elements in that array are unique or not, if there are duplicates, if 2 of the elements are the same or not in that array. Remember, we have method 1 and method 2. We compare 2 methods, method 1, method 2. All right. Method 1, remember, it's the brute force method. So we do comparisons immediately. Yeah. But we need to do global comparisons, method 1. So method 1, so we use global comparisons. So the final result, big O of n squared. Efficiency, big O. Method 2, we sort it first. We organize the data first. Then, after that, we do adjacent comparisons. Then, because sorting, you need to use big O of n log n. Sorting. Adjacent, you just use big O of n. But this part is dominant. So method 2 is better than method 1. All right. If I ask you, can we do better than method 2? One question. Can we do better than method 2? Right? Yeah. So method 3. if you use this hashing technique, then you can do better. You can do better than method 2. Hashing technique. Okay? Yeah. So the hashing big O of n. You can solve this problem. Big O of n. Okay? Yeah. So you can see, very important, this technique. All right. Yeah. I remember, so this question is a question used in interview for some companies. Yeah? Some companies give algorithm interview questions. Many, especially many top tier companies, they give a lot of algorithm questions. Yeah. But this question is a relatively simple one. Yeah, because there are different levels, hard difficulty levels. So this is a relatively simple interview questions they used. Yeah. So if you answer this question, you should use the hashing technique, the best algorithm to solve this problem, hashing. Yeah. So now let me talk about this hashing technique. Idea is very simple, yeah, but very effective, very powerful. All right. How to find data item with a given key? It's a search problem. Hashing technique is used to solve a search problem. You have a given key, and your data is stored in an array. So now you want to use some fast way to find the given key. All right? Yeah. But for hashing technique, so usually you need to do a lot of search operations, not just one. Yeah. If you do only one search operation, it may not be efficient. Yeah. Because your building cost is pretty high. You build the hash table data structure. Remember, it's advanced data structure. So we need to learn some advanced data structure. It's called hash table data structure. So you spend a lot of time to build that advanced data structure. Then you need to use it to do many search operations. Then you can get your investment back. Otherwise, not worth it, right? Yeah, otherwise not worth it. All right. Give a collection of data dynamically, yeah? Especially when you have dynamic data, right? Your data keeps coming in. You need to add it into your data structure so your hash table can, take the dynamic data easily. Yeah. So that's another good property for this data structure. Each data item is identified with unique key. Yeah. So that's the basic requirement. Yeah. There is ID. Yeah. Each data item, there is ID, unique. Yeah. How to make your data search efficient? Yeah. All right. Data structure not a given. Yeah. So because to solve this general problem, you have a lot of freedom to choose your data structure. Yeah. So you want to, take advantage of that freedom to design some efficient data structure. All right. Right. Okay. Yeah. So let me do some comparisons here. Related to the search algorithms, we learned linear search, binary search. But there is another search. So we didn't learn in class. But it's a very simple. Very simple. So I put it here, called index search. Index search. So I put it here for comparison. The data structure, linear search array, binary search array, index search also array. Performance, linear search big O of n, binary search big O of log n, index search extremely fast, big O of 1. Why so fast? Because what's the index search? Given an array, what's your search key? The search key equals array indexes. So you use array index as the search key. Directly. Okay? Yeah. So in our textbook, it's called direct addressing. Yeah. Our textbook, another name. Yeah. So in some older textbook, it's called index search. In our textbook, it's called direct addressing. Yeah, because the address is direct addressing method. All right. Given search key, you have the array index. Then you find that location in the array immediately. That's big O of 1. Extremely fast. But it has a big problem. So that's why nobody uses this method in the real world. Useless. Because its drawback is huge. Too big. Hard to overcome the drawback in this index search. All right. Ordering, unsorted the data. Binary required sorted data. Index search unsorted. Dynamic, linear search. So you can add dynamic data because you don't need to maintain the order, right? Yeah. Binary search, dynamic data, if you want to recover the order information, order, it's very expensive. All right. Index, because you do not need to maintain the order. Yeah. The reason it's costly because you need to maintain the order. Otherwise, the next round binary search, you cannot apply next round binary search. Yeah. All right. Efficient sorting, because sometimes people need to sort the data. Yeah. So in the array, because you do not maintain the data ordered, if the business requirement needs sorting, then you need to sort it. Then it's not efficient. For the linear search case, you need sorting is costly. Binary search, because you maintain the order, right? Maintain the data order. So you can provide ordered data immediately. Yeah. For other cases, no. Yeah. All right. Then the new algorithm. So based on the these three, the properties of these three algorithms, the new algorithm, we want to get data structure. We need a new data structure. Efficiency, we want to have this fast efficiency, big O of 1 efficiency. Yeah. Not sorted, because sorting very expensive. So we don't want to do the sorting. Yeah. Dynamic, yes. So we can add dynamic data easily. Yeah. Because we do not require data ordered. So it's very easy to add dynamic data. Yeah. Efficient sorting, no. Yeah, because there is no order maintenance part in this data structure. Yeah. All right. Then, so you can see this new method actually borrows a lot of properties from this index search. Index search has a big drawback. But this new method target the drawback of this index search. It used some smart idea to overcome the big drawback of the index search. Then it is a good, efficient search algorithm. All right. Now let's look at what's the main idea it uses. Generalized idea of index search. First, we need to know the big drawback, right? Yeah. So, direct addressing. So that's another name of the index search. All right. Key property in this algorithm. You do the mapping from key to index of array directly. So that's why this name. You do not do any change on the original key. You just use the given key as the index of the array. But this property has a big problem. You need to look at this key, because in real-world applications, many times the keys are quite long. Usually, the keys are long, very long. Yeah. But if you want to use long keys as the array indices, then your array will be very large, right? Yeah. But the elements in your data, not too many. The key is long, but the elements, not that many. In that situation, if you use keys as the indices of this array directly, you will waste a lot of memory space, because you only use a small portion of your array. That's the reason this method is useless. Nobody uses this index search. Useless because of this problem. Wasting too much memory resource. How to fix it? Next, we want to look at the simple idea. The fixing idea is very simple. So let's learn how to use space efficiently. The key is too long. The question is how to make a long keys short. If you can make a long keys short, then you can use this method, right? You create an array with these keys as array indices. Then you won't waste a lot of memory space. That's a quick fix, right? So the question is, the main question to solve this problem, you need to convert long keys to relatively short keys. Yeah. Long keys, for example, social security numbers, student numbers, usually many digits, right? You cannot imagine using those numbers as array indices. Too large, not efficient, wasting a lot of memory space. For example, here, social security number or student number, 7, 3, 9, 8 number of digits. But suppose we only have 40 students. Yeah. And you cannot create an array using the student number as array indices directly, wasting too much memory space. Yeah. All right. To solve the problem, we want to find some way to make the keys shorter, much shorter. Yeah. Because 40 students, we just need locations slightly greater than 40. cannot be less than 40. Yeah. Equal 40, theoretically possible, but too tight, right? Too tight. So you need some room. You need some breathing room to manipulate your data. So ideal situation, so you want some slot numbers to hold your data slightly not larger than the number of data items. Yeah. Question, we want to map keys to slots. There is a mapping process here. How to do the mapping? If you can find a good way to do the key mapping, then you have a nice solution to your search problem. Nice solution. All right. Mapping strategy. What is a good mapping strategy here? Fast calculation. Because when you do the mapping, typically you do some calculation, right? Yeah. So you apply certain special functions and do some calculations. So you need to make sure the calculation is very fast. You don't want to waste time on the mapping part. All right. Evenly distributed among all the slots. This requirement important for the efficiency, but not easy to achieve. Evenly distribute among all the slots. Because after the mapping, you get a location, numbers, you need to arrange your data there. If your data mainly focus at some small portion of the storage locations, then your overall performance will be very slow, because you need to resolve a lot of conflicts. There are many conflicts you need to handle. Yeah. So I will talk about that later, that concept. So slow. So you want to spread out evenly, spread out on all the locations. So then you can get a good overall efficiency. Not sensitive to any pattern, because sometimes the data may have certain pattern. So if your mapping strategy is not robust against those patterns, then your performance, the overall performance, will be very slow. Yeah. So you can see, in order to find a good mapping strategy, you need these three main considerations. Yeah. All right. Implementation. Now we need to really look at how to make it happen. Yeah. All right. Choose appropriate math functions. Mapping by math functions. The question, what are good math functions to use for this purpose? Okay. All right. So if you can find good math functions in this situation, then your solution is almost there. Yeah. All right. So we call these functions hash functions. Hash functions. These special math functions, hash functions. Yeah. Then we talk about in this here, very short time, we only talk about two simple hash functions. The first one, division method. Second, multiplication method. Yeah. Today, we only have 5 minutes left, so I talk about division method. Next time, I use 10 minutes to talk about multiplication method. then another 10 minutes for the collision problem. Because when you do hashing, you need to deal with a lot of collision cases. So I need to talk about that collision problem a little bit. So then we complete the topic. All right. Hash function design, division method. Assume that all keys are natural numbers. If the keys could be strings, right? But string, if we convert strings to numbers, it's very easy, right? Yeah. So that kind of conversion, very easy. So for simplicity, we just use natural numbers here. Right. Yeah. There are m slots. This is the simplest hash function. The number of slots, assume m, yeah. Then our key k very large. Now we do the mapping. Yeah. So the first simple way for the mapping, h of k, we just take k mod m. We use the remainder as the hash value of this key. Yeah. Remainder, k mod m, this is the remainder. We use remainder as the, shorter, much shorter key, right? Yeah. The slot number. Yeah. But this method has a lot of problem. It's easy, yeah, but it's not a good one in general. So we need to do a lot of improvement on this method. So this is our first try. First try is this one. Not good. Yeah. So in order to make it good to use, so we need to improve quite a lot. All right. Yeah. Yeah, because so many problems here. Depends on the keys. Yeah. Not robust. Yeah. So when you have some special patterns, you can break it easily. Yeah. So you will get a very poor efficiency for this method. Yeah. Yeah. Here I have some simple example. Yeah. So I hope I can finish this example before the end of this class. Yeah. All right. Short example, m equals 15. Yeah. So small number, I just show you the idea. Okay? 15 equals 3 times 5. Yeah. All right. If we mod this 15, k mod 15, then you can see there is one simple pattern that can break this method easily. The pattern is if the keys k is a multiple of 3. If our data happen to be multiple of 3. Yeah. So many data items, multiple of 3, then h of k is also multiple of 3. Yeah. Because you do division by 15, this divisor multiple of 3, so your remainder is also multiple of 3, right? Yeah. Remainder is, because, here, yeah. Think about, this is a remainder, all right? K, original key. You do division by 15, right? Division by 15. Quotient is n, all right? Quotient. Then you have remainder, so your remainder equals this h of k. So k is a multiple of 3, 15 times n multiple of 3, then the remainder is also multiple of 3. Yeah. Based on that, so your hash keys can only be multiples of 3, then what's the consequence? What's the consequence? Yeah. Yeah. So I just tell you the consequence. Because you can only use the elements with the location numbers multiple of 3, then that means only 1/3 of the slots can be used for this pattern. The remaining two-thirds of the slots are not mapped. Not mapped directly. Okay, not mapped directly. Okay. Yeah. What happened next? Because that means you have a lot of collision. Yeah. So the slots only 1/3. So you map all your data to this 1/3. Okay, 2/3 not mapped directly. Then you need to resolve all the collisions, move, all the elements to. Then you need to do a lot of work. That means it will be very slow. You need to spend a lot of time to resolve a lot of collision problems. All right? Yeah. So then it's a not good method. Yeah. All right. So let me stop right here.